This first session is a theme focused on socio-hydrology, and you can read this in the program. We have 4 speakers. We're very fortunate to have a kickoff by Wouter Buytaert. Wouter's a reader in hydrology at Imperial College, London, Howard's former abode. Wouter did his PhD with Keith Bevan a little over 10 years ago now, I think, at Lancaster. Postdoc, sorry, with Keith Bevan a little over 10 years ago. And he's really emerged as a thought leader in this area of socio-hydrology. He's editor of HES, one of our flagship journals, and I know Wouter from his work particularly in the tropics and subtropics. And he has a passion for the Andes and linking, I think, networks of observations with things that really help with poverty reduction and addressing First Nations, particularly in the Andes. Today we're going to hear a little bit about his work with monitoring socio-hydraulic systems, focusing on sensor networks and governance. And if we could bring his slides up, that would be great. And I will turn the stage over to Wouter and start my timer. Okay.
Thank you very much indeed. It's a great pleasure and a great honor to kickstart this conference. I really feel a bit humbled. But I would like to use this opportunity to become a bit philosophical, given that the idea is to kickstart some discussion and maybe even be a bit controversial. But essentially going back to the basics, the foundations of discovery science, the raw material of hydrology, monitoring observations, and in particular in situ observations. Because indeed there is a lot of technological advance in remote sensing, satellites going up all the time, generating ever-increasing data sets that stream in, that need special big data technologies to be processed. But at the same time, I think that few of us will disagree that there's still a dire need also for in situ observations, not just as a way to ground truth and calibrate remote sensing and satellites, but also because many of the hydrological processes that we study are still very hard to monitor with satellites. Think about rivers, think about groundwater, and all that. So I would like to argue that perhaps in hydrology we haven't been as good as we can be in collecting in situ data, or indeed that hydrology, if you compare to other natural sciences, is still very much a data-scarce science with limited amount of data and with limited quality of data. And I think that most of us are familiar with dramatic graphs like this one from the Global Runoff Database, showing the data availability of runoff data around the world, showing this dramatic peak several decades ago, and then the rate of observations declining after that. And of course, there's probably a technical reason, the lag time that it takes for an observation to get into a database like this one. But on the other hand, there is quite a bit of indications that in many places in the world, the monitoring systems and the monitoring networks are actually declining, or at least that is the case in the UK as a result of funding cuts, as a result of ecological requirements, that there's actually more waste, for instance, being taken out than there are coming. So a bit of a worrying trend, and one that we might want to think hard whether there's a way of reverting that back. Is that in terms of data from a statistical perspective, that actually the sampling density of many of the processes, think about the area that we cover with rain gauges compared to the total area of a catchment is probably only a billionth, which is a ridiculously low statistical sampling density. And even the data we manage to collect are often very, very uncertain. And this indeed is a graph that I stole, I think, from Howard's lecture notes when I inherited them, came to Imperial, who might also have been Neil's. But I think it's a graph that's very familiar to many of us. Indeed, any hydrologist worth their salt has spent hours, if not days and months, trying to make sense of time series of like this one, discharge with obvious artifacts, which obvious data gaps, and with the difficulty of trying to trace back what actually happened with those artifacts, what lays behind, without often information about the sensors, about the method that was used, about the stage discharge curve that has been that has been used to convert water level data into discharge. And without that, it's indeed very, very difficult to get to grips with the potential uncertainty and indeed the quality of the data that we work with. And unfortunately, those are quite typical graphs, especially for those of us that work in developing countries and in places with less than ideal monitoring. Or to put it a bit more bluntly, as I do to my students, mankind is about 1 billion times better in observing and measuring the distance between the Earth and the Moon than it is in measuring the river flow of the Thames in London. So I think that puts it a bit into perspective and is a call to highlight the importance of really trying to get better data, given that they are the foundation of anything else that we do, the input into models and all that. So that is the problem. Now, what are potential solutions? Well, if you think a bit about it, then it becomes obvious that actually the biggest bottleneck is not so much technological. Indeed, the amount of data that we collect with a typical sensor is well within the technical possibilities of data storage, transmission. Many of the sensors aren't really rocket science. It's just a matter of trying to find a way of putting them there, of maintaining them, and highlighting the value that they create for society. And of course, technology helps us there with ever-increasing quality and robustness of and lower cost of storage technologies. Think about Arduinos, for instance, very low-cost loggers that you can build from those. Data transmission networks, global mobile phone coverage, and all that. So a great opportunity with lots of buzzwords. Think of Internet of Things, think of big data and all that we can leverage, and indeed many people are leveraging, but where perhaps we can even do a better job. And for those of you who wonder how you can use a Tesla for hydrological measurements, my answer is, I don't know. If you have any ideas, I'd be very happy to know, and I'd be very happy to put one in the budget of my next grant proposal. But jokes apart, there is obviously, it's a good example of a billion-dollar industry, self-driving cars with lots of technological innovation, and perhaps an opportunity for hydrologists to try and think how we can leverage those advances to drive our own agenda. And that is exactly what we try to do in a small project in Imperial. Those self-driving cars, they're full of sensors, distance sensors being one of the main ones that don't want to bump into other cars. And our distance sensor, with a bit of tweaking, can actually be used to measure water level. Indeed, it's the most important proxy to discharge, and also something you need to measure groundwater wells, boreholes, and all that. So we developed a very low-cost water level sensor. Again, no rocket science, but the fact that it's much cheaper, this version is about $200, and we're confident we can bring that down to perhaps $50 or even less in the foreseeable future, and allows us to address some of those black spots in monitoring that still exist in big parts of the world. And that's what we've been trying out in contexts as diverse as monitoring or a flood risk assessment in Nepal, evaluating green infrastructure investments in the Andes, or monitoring groundwater and drought in Somalia. So simply a way of using robust and low-cost technology to increase the amount of information, but it also opens up lots of interesting questions about what you can do if, for instance, you network those sensors, synchronize them in real time, install an entire array in a river at high resolution, minutes or even second, and what that allows you to do in terms of, for instance, monitoring the celerity of a flood wave coming through, using that in hydraulic modeling, and et cetera, et cetera. So technology providing a great opportunity there to think outside the box, to think about new ways of monitoring. But let me zoom in a bit in the example of Somalia, indeed a region that is in dire need of better data for things like drought forecasting and drought alleviation, but also the place where probably you don't want to install a very expensive piece of kit for the risk of damage. So where low-cost technologies are ideal, and that's what we tried out in Somaliland, the slightly safer part of the country, to work with an NGO concerned worldwide to monitor boreholes and to see to which extent we can extract useful information to improve drought early warning. And here's just an example of what our low-cost sensors managed to achieve. Very high resolution, in this case 1 minute measuring of the water level. And the groundwater experts under you can already see that it's almost like a drawdown experiment with a very nice recovery afterwards. Almost, here we are. So the drawdown for water extraction from the well, and then the recovery, another drawdown, and another recovery, which is almost a textbook example of how a well should behave from a groundwater perspective. So great opportunities to look at groundwater dynamics, which is indeed what I'm trying to do now with my colleague H.M. Butler, but also an opportunity to, for instance, look at how much water is being used. You can almost perfectly see when water is being taken out. If you combine it with the well diameter, you can calculate how much water is being taken out, how frequent, even the time of the day, and all that, if you like. So indeed, it gives a lot of information, not just about the hydrology, but also about the way that people interact with the water cycle and use water resources. And that brings me to the bigger topic of this session, socio-hydrology, because indeed technology doesn't only allow us to measure hydrology, but very many other aspects of the socio-hydrological system. I've given an example here of sensor networks, but think about drones, great opportunities to bridge the spatial scale between a point observation and large-scale satellite-based monitoring. Social media, especially useful to look at how people react to events like a flood or a drought. Local expert knowledge, which indeed is receiving more attention and which, through the use of ICT and mobile phones, gets well beyond the local level and makes it much easier to access and to try and integrate. So great opportunities for new and novel sources of information, but also great opportunities for new actors to break open this rather confined and almost monopolistic space of monitoring, as has been in the past, where hydrological data and hydrological monitoring is very much the task of government institutes such as the Environment Agency in the UK. Indeed, low-cost technologies allow NGOs like Concern in Somalia to set up their own monitoring network, allows even participatory monitoring, communities like in the Andes, as we've done, or even citizen science is indeed very strongly driven by the availability of low cost and robust sensors for which you don't have to be an expert to use them. So also there, what we'd call a diversification, both of the sources of information, but also who collects information and for what purpose. And that very nicely maps onto or opens up further questions about water management and governance. Indeed, if new people can collect information, generate scientific evidence, and use that to drive an agenda to increase things like accountability, or even to influence governance and decision-making, then that has potentially very big impacts in the way that water resources and water-related risks are being managed. And we actually see, working with social scientists on this topic, an almost convergent evolution between some of the thinking in social science about governance and, for instance, polycentric management of water resources and management of common pool resources on the one hand, and technological diversification and decentralization on the other, with new people coming in and new actors playing a role. And in a way, you could argue that, for instance, the internet is the paradigm almost of a polycentric and distributed system. So different evolutions that go in the same direction, and that are worth exploring how we can manage them to improve the way that the water cycle is managed for the benefit of mankind and to reduce the risks that it poses to sustainable development. So that was a very quick overview. Again, some ideas that hopefully spark some interest and are interesting enough to continue discussion. But that's all that I'm going to say for now. Rest me only to thank the very many counterparts and colleagues that we work with in a very interdisciplinary and interesting context, and also, of course, to thank you for your attention and hopefully for discussion afterwards. Thank you very much.
So again, we have a half hour built into the program at the end of the 4 talks, but just wanted to see if anyone had a question or two now as we go through the morning. We'll obviously need more caffeine this morning. John?
Wouter, thanks for the talk. The co-creation of knowledge, when you have multiple cultures in a river basin, I wonder if you could elaborate about how do we do that? This is a very relevant issue for Canada, and I know you've experienced this in the Andes as well.
Yeah, I think on that topic I talk more from personal experience of trying to do that rather than really a scholar on that topic, leave that to the social scientists. But it's very interesting to interact with them and to experience potential ways of doing that. I think one of the key elements is interaction, iteration, and constant reinvention, if you will. There isn't a magic bullet of this is the way to indeed implement knowledge co-creation, but I think one of the things that I've seen, and obviously being an engineer, I'm probably a bit biased towards the use of technology, but one advantage of those low-cost sensors is that it gives a very concrete starting point of discussion about what you can do with technologies, what is the meaning of data, how do they indeed integrate in a much wider context of knowledge, which goes much beyond science and hard data. But it's a starting point to really have a very open discussion about how different people and different actors have different agendas, do things in a very different way, and starting thinking about how you might want to reconcile those different interests and ways of doing things. But that's, again, very much from personal experience rather than a very solidly scientifically proven methodology. So still a lot of work to do, I would say.
I like the use of these low-cost sensors very much, in particular the connection to social science. My question is, how do you see the potential for linking up what you can observe at very small scale, as you show, to larger scales where we then have other kinds of measurements, so that you have a cross-scale observations, because there's, of course, this is a very small scale, and a much larger scale where you then have other measurements. So how do you see the opportunity for making that connection?
Maybe repeat the question just briefly, if you could.
Yeah, so the opportunity of the technology to scale up or to help the problem in hydrology of scaling from point observations to a larger scale. Well, I think one very concrete opportunity I see is to increase dramatically the density of observations. Of course, water level by very definition is a point scale, or in many cases is a point scale measurement. You can try and find a different way of measuring that covers a larger area. But another thing we could do is simply have many more orders of magnitude more of sensors. If you will, a bit of a vision perhaps might be, what if we could install a water level sensor under every bridge or river bridge in the UK? Something which is technically feasible, is probably even financially feasible, and would increase the density of measurements dramatically, many magnitudes. And so what if you have such a data set that provides you minute or even second resolution water level data at such a large scale? How would that, what can you do in terms of upscaling? And I think that the opportunities are tremendous.
One last question from Al, and we'll move on.
Actually runs a hydrometric network. Water level's great, but it's the least expensive part of my operation, right? So for Canada, if I only had to do water level, my life would be easy. Unfortunately, the real calculation is flow, right? And that's the difficult part of what we do. So flow is an estimated value. We use the water level to infer the actual flow, and we have to go and take measurements and recalibrate our curves, and that's where the real expense is, right? So just want to make sure that that's clear, that the real expense is deriving flow from water level information. It's not actually measuring water level. So although I applaud what you're trying to do, it's great. It works great on floods. It works great during low flow situations. To actually derive a flow estimate is a little more complicated than that. So just let's keep clear on that.
Yeah, no, I can't agree more, and then perhaps that was the controversial aspect of the talk. Obviously, it's not a panacea, but just some starting ideas for that kind of discussion. But then on the other hand, there are many other activities ongoing about, for instance, measuring water flow or flow velocity using cameras and using other methods. So you can start thinking about how perhaps you use them, you combine them as a way to start piecing together different pieces of the puzzle. But yes, it surely isn't the final solution to all hydrology. I'm very well aware of that.
Thank you very much. All right, before I introduce our next speaker, I just want to acknowledge our two rapporteurs. And maybe they could just stand up and wave their hand, especially so our four speakers can see them and hopefully promote some interaction at the